Hello guys, welcome back to my channel. And I would like to remind you, if you don't know, I'll tell you in that case that I've restarted my high school calculus series. So in the last video we talked about the rules of finding derivatives. The basic techniques like the product rule, the chain rule, the quotient rule, and all those rules that we need to find out complicated derivatives. So I'm assuming you watched those videos, or you probably know the rules well, because in this video all the derivatives that we are going to do, not going to write as many steps as the previous video. So please be thorough with your derivatives and what rules to use when we are differentiating a function. So as always, let's get to it. So unlike the previous video where we just differentiated what was in front of us, without just thinking what rule to use directly, now we must learn how to work smart. We must learn how to sort of play with the function that we have to differentiate, so that we come up with a way simpler expression that is easier to differentiate than before. So as an example of that, we have the function y equals the square root of secant of x plus 1 divided by secant of x minus 1. But what's the secant of x? It's 1 divided by the cosine of x, right? Plus 1 divided by 1 over the cosine of x minus 1. So why don't we just cross multiply in the numerator and the denominator? So we'll have 1 plus cosine of x divided by cosine of x times, well, we're now writing the denominator, but we'll have to write it as a reciprocal. So cosine of x was in the denominator of the denominator. We have 1 minus cosine of x here. So the cosines cancel out proudly, and we have 1 plus cosine of x divided by 1 minus the cosine of x. But what is 1 plus cosine of x? We have an identity for that. We can use the half angle formula for the cosine to end up with 2 times cosine squared of x by 2. The angle gets halved. And what's 1 minus cosine of x? Again, we can use the other version of the half angle formula for the cosine. Then we end up with 2 times, this time sine squared of half the angle. So the 2's cancel out. We have a cos squared and a square root of that. So we just have a cos of x by 2. And the same thing here, sine squared, and root of that is sine of x by 2. But what is cosine of an argument divided by the sine of that argument? That's right, cotangent of that argument. Here the argument was x by 2. So you see, instead of being left to differentiate this part, this radical of secant of x plus 1 divided by secant of x minus 1, we can simply reduce our y to a cotangent of x by 2. And now we can get ready to differentiate. So we do these manipulations before differentiation, just to get a better version of y. And when we got a better version of y, then we differentiate both sides with respect to x, so that we end up with dy over by dx on the left hand side, and the derivative of the cotangent of x by 2. So again, chain rule. So what's the derivative of the cotangent? It's negative cosecant squared of whatever was inside x by 2 and multiplied by the derivative of x by 2 is going to be just a half. And I really hope that you practiced your chain rules, because I'm not going to show all the steps. I'm not going to necessarily explain every chain rule that we encounter. So in case at this point you're wondering what's going on with this derivative, how did we get this half, how did we get a cosecant squared of x by 2, please refer back to my previous video and you'll get a sense of what's going on. Okay, let's do another one now of working smart, another examples of how to work smart. So now we have a function y being defined as the square root of x squared plus 1 minus x divided by the square root of x squared plus 1 plus x. So just jumping to calculate the derivative is going to be really hard, and it's a real pain, I'll tell you that, because first there's a quotient rule, then there's a chain rule for the radical, and it's going to be pretty messed up. So let's just work smartly as the section suggests. So look at the term with the radical plus or minus a variable. This looks like it's going to be an excellent candidate to use rationalization. Well, how do we rationalize? What we do is we take essentially the same thing as the denominator, but we introduce a small change. Instead of the plus x, we have a negative x, and since we have to maintain the equality, we have to do the same on top too. And this is what's called the conjugate of the denominator. So now we have basically this expression squared. We have x squared plus 1 minus x, but the whole thing squared now, divided by, we have square root of x squared plus 1 plus x multiplied by the square root of x squared plus 1 minus x. Well, let's square this up properly. So we end up with the square of this radical, which is just the inside terms, x squared plus 1 minus 2 times x times the square root of x squared plus 1 plus x squared divided by, now we can use the difference of square identity, but this is basically a plus b times a minus b, that becomes a squared minus b squared. So that's the difference of squares identity. So we have the first term squared, which is just going to be x squared plus 1 minus x squared, so x squared. Now the wonderful thing is x squares cancel out, we are only left with a 1 in the denominator. So essentially we got rid of the denominator completely. Isn't that fabulous? So y is just going to be x squared plus 1 and another x squared, so 2x squared plus 1 minus 2 times x squared plus 1 under root. Well, see, no denominator, no quotient rule, everything is just simple to differentiate. So let's differentiate both sides now with respect to x. We have a 2 as a constant, and the derivative of x squared is 2x, so 2 of 2x is 4x, derivative of 1 is 0. Now we're going to have to use the product rule, it seems, for the derivative of 2x times the square root of x squared plus 1. So we have 4x minus, well, the 2 can be taken out. Let's make x weight and differentiate square root of x squared plus 1 minus, well, 2 is outside. let's make the square root of x squared plus 1 weight while we differentiate x. Well, the derivative of x is just 1, so this goes to 1. We have 4x minus 2x. Now we can use the chain rule. So the derivative of the square root was 1 over 2 times that same square root. And now by the chain rule, the derivative of x squared plus 1 is going to be 2x. Derivative of 1 is 0, as I said. And we have negative 2 times the square root of x squared plus 1 here. So one of these 2's are going to cancel out, and we end up with 4x minus 2x squared divided by x squared plus 1 minus 2 times square root of x squared plus 1. Okay, so now we come to an interesting part that's called using standard substitution. So what's the standard substitution basically? It's substitution is all about trigonometry, in the sense that, say you have an expression of the form a squared square root of a squared minus x squared, or without the root, say a squared minus x squared, then the substitution that you should look for is let x equal a sine theta or a cosine theta. And you know why? Because why don't you just plug that in over here? So you'll have a squared minus x squared is a squared sine squared theta. So a squared minus a squared sine squared theta, using the square identities of trigonometric functions. Well, let me just show you the working here for the first one. So we'll have a squared minus a squared sine squared theta. You'll just end up with a squared can be factorized out, and you'll have 1 minus sine squared theta. That's cosine squared theta, right? So you finally end up with a times the cosine of theta. And if you substitute x as a cosine theta, you'll end up with a sine theta. So that's why when you see something of the form, so let's call this standard substitution number 1. If you see something of the form a squared minus x squared or a squared minus x squared without the radical, you go for this substitution. Now standard substitution number 2 says that if you have something of the form square root of a squared plus x squared, or if you just don't have the root at all, so you don't have the root at all, a squared plus x squared, then you go for the substitution x equals a times tangent of theta or a times cotangent of theta. You know why? Because if you plug that in, you have a squared plus a squared tan squared theta. So taking the a squared common, we'll have 1 plus tan squared theta. But what's that? Secant squared theta, right? So we'll end up with a times secant of theta. And the same thing for the cotangent, you'll end up with a times a cosecant of theta. Okay, so standard substitution number 3 says if you have an expression of the form square root of x squared minus a squared, or just lose the root x squared minus a squared, then you go for the substitution x equals a times secant of theta or a times cosecant of theta. And you know why? Because again, if you plug that in, you'll have a squared secant squared theta minus a squared. Factorizing the a squares out, you'll have secant squared theta minus 1, which is nothing but tangent squared theta. So a squared times tangent squared theta, which finally turns out to be a times the tangent of theta. Same thing with the cosecant of theta. You'll end up with a times a cotangent of theta. And the reason these standard substitutions are important is because, say if you have a weird function, function of any one of these forms of, say, type 1, type 2, or type 3 inside an inverse trigonometric function. Say you have a tan inverse of one of these, or sine inverse of what we had for number 3, then you know that you want to go ahead with the standard substitution. And I'll show you in a minute how helpful that is. And I would also recommend you guys to remember this substitution, because it will be useful when we are doing integration, when we are doing integral calculus, because we have an entire series of family of integrals that can best be calculated using trigonometric substitution. So I would encourage you guys to actually remember these types of substitutions, or basically just know these are basically observations. These aren't even theorems or like rules, but these are observations that if you have something of, say, type 1, you use this kind of substitution. You have something of type 2, you use this kind of substitution. If you have something of type 3, you use this kind of substitution. So I would encourage you to just observe and remember what kind of substitution to use when. These are great tools when it is going to come to integration, and also further in this video when we actually use them. I'll show you in a minute. Okay, as I said, it's standard substitutions have more to do with inverse trigonometric functions. So if you have y equals the inverse sine of x over square root of x squared plus a squared. Well, forget the numerator for now. Look at the denominator. You have an x squared plus a squared term. Well, what does that remind us of? Standard substitution number 2, right? And what should we use? We should let x equals a times tan of theta, because if you plug that in, you have a squared tan squared theta, which will end up in a squared secant squared theta, right? Because we had a identity tan squared theta plus 1 is going to be secant squared theta. So with that principle in mind, we're going to actually use that substitution. So we're going to have y equal this inverse sine of, well, what's x? A times tan theta divided by the square root of a squared tan squared theta plus a squared, and we end up with the sine inverse of a times tangent of theta divided by, well, we can take the a squares common. We'll have tan squared theta plus 1 under a root now, and that's going to give us sine inverse of a times tan of theta divided by, well, tan squared theta plus 1 is secant squared theta, right? We established that fact. We're going to have a squared secant squared theta. Well, we can actually just get rid of the square root and the square. We end up with a times tan of theta divided by a times the secant of theta. The a's will cancel out proudly, and so you finally have y equals the sine inverse. Why don't we write the tan in terms of sine theta divided by cosine theta, and we also have a secant theta in the denominator. But a secant theta is 1 over cosine, so that cancels out with this cosine. and you finally end up with sine inverse of sine of theta. But if you have the inverse of a function containing the function itself, you end up with the argument, or theta in this case. So it's basically like the sine inverse and the sine are going to cancel each other out. You end up with theta. But theta is a variable of substitution, right? We only know x's and y's. So let's back substitute now. What was theta? So we know a fact that x is equal to a times the tan of theta. So we know that x by a is nothing but the tan of theta. So theta is going to be the inverse tangent of x by a. So our y is going to be the inverse tangent of x by a. And now let's just compare what we had before and what we have now. Before we had x over sine inverse of this crazy quadratic mess, and now we just elegantly end up with the inverse tangent of x by a, which is way easier to differentiate. So you see how powerful this technique is. Well, now we can differentiate with respect to x. So dy by dx is going to be the derivative of the inverse tangent of x by a. So chain rule again, 1 over 1 plus variable squared, so x by a squared times the derivative of x by a. It's the chain rule, remember? So you end up with cross multiplying a squared divided by a squared plus x squared times the derivative of x by a is going to be 1 by a. You can cancel one of the a's out if you want. So you end up with dy by dx is equal to a divided by a squared plus x squared. So you see how clean and beautiful this method is. That's using standard substitution for you guys. And this process of cleaning out these inverse trigonometric functions by using standard substitution is going to be very handy when it comes to integral calculus. So please don't forget this, keep practicing it daily. So let's do another one. We have y equals the inverse tangent of x over square root of a squared minus x squared. So one hint for using standard substitution should be the inverse trigonometric function up front and a weird quadratic like thing under a root, or sometimes it won't even be under a root. Well, looks like we are gonna have to use standard substitution number 1. That said, let x equals a times the sine of theta, and we'll see in a minute why that's so powerful. So we have the inverse tangent of what's x, a times sine of theta divided by square root of a squared minus a squared sine squared theta. Now I won't show all the steps, so we end up with inverse tangent of a times sine theta divided by the square root of a squared cosine squared theta, which can be written as the inverse tangent of a times sine theta divided by, getting rid of the square root, a times cosine theta. The a's cancel out, and what is sine theta divided by cosine theta? Tan theta, right? Inside an inverse tangent. So inverse tangent and the tan are sort of going to cancel out. They're inverses of each other. So you end up with y equals theta again. But what's theta this time? Well, we know that sine theta is nothing but x by a. So theta is going to be the sine inverse of x by a, right? So let's just plug that information. So y is nothing but sine inverse of x by a. So people, we have to do another chain rule here, just like last time when we differentiate with respect to x. So we have d over dx of inverse sine of x by a. So we end up with 1 divided by the square root of 1 minus variable squared, so x by a, the whole thing squared, times the derivative of the inside function of x by a, chain rule. We can certainly cross multiply. We get a squared minus x squared divided by a squared under a root which can be taken on top. The square and the root cancel off. We just get a divided by the square root of a squared minus x squared, that's still under the root, times the derivative of x by a is just 1 by a. The a's are going to cancel out, so we just end up with dy over dx is nothing but 1 over the square root of x a squared minus x squared. So you see how fantastic this thing is. So let's do a different example that can be said to be loosely based on our standard substitution that I discussed. So we have cot inverse of the square root of 1 plus x divided by 1 minus x. Well, we don't have any squared terms, so it doesn't fit into our the three standard substitutions that I discussed a while ago. But if we let x equal cosine of theta, let's just try this, and you'll see in a minute why I use this. So we have inverse cotangent of square root of 1 plus cosine theta divided by 1 minus sine theta. Well, what is this? What is 1 plus cosine theta? Well, I did a similar derivative question based on the 1 plus cosine theta 1 minus sine theta identities, basically the double angle formulas for the cosine. So we can actually write this as inverse cotangent of square root of, well, what's 1 plus cosine theta? That's 2 times cosine squared of half the angle theta by 2 divided by what's 1 minus cosine theta? That's 2 times sine squared of half the angle theta by 2. The 2's cancel out proudly as always. So we have y is equal to inverse cot of square root of cosine squared of theta by 2 divided by sine squared of theta by 2. That becomes inverse cot of square root of, well, cosine squared theta by 2 divided by sine squared theta by 2 is cot squared but theta by 2. The angle is retained basically, so you can get rid of the root because of the square, and so you end up with cot inverse of the cot of theta by 2. And like our previous example, these inverse functions are just gonna sort of annihilate each other mutually and gonna end us with theta by 2. But what's theta? Well, we assumed our x to be cosine theta, so theta is just gonna be cosine inverse of x. So we have y being equal to cosine inverse of x divided by 2. Now let's differentiate both sides with respect to it, because we simply have a cosine inverse of x, which is way easier to differentiate than this this complicated square root that we started with initially. So differentiating both sides with respect to x gives us dy by dx is equal to, half is taken outside, the derivative of inverse cosine, so that's going to be negative 1 over 2 as it is times 1 over the square root of 1 minus x squared. It's basically derivative of the inverse sign but with this negative sign. So that's really elegant. So you can, if you want to call it a standard substitution, you may include that in the list of the three standard substitutions. That if you have a 1 plus x or a 1 minus x kind of expression, that's when you use x equals cosine of theta because of the double angle formula on the cosine. Nice. Okay, so here's what I call completing a formula, or you can call it the deceptive kind, which if you don't know your formulae well is really hard to do. So these functions look like they can be done using our standard substitutions, but once you plug everything in, then you just end up with bigger mess than you started with. So let me give you an example. So we have y equals sine inverse of 2x divided by 1 plus x squared. Well, now this is sort of can be looked at as being of this deceptive kind and also of the kind of the standard substitution, because here a standard substitution will work. So because of 1 plus x squared, you might say that let x equals 1 times tan theta. So just tan theta. Once you plug that in, you get sine inverse of 2 times tan theta divided by 1 plus tan squared theta. But what is this thing? We had a formula for sine of 2 theta as 2 times tan of half the angle. Half of 2 theta is just theta, so 2 times tan theta divided by 1 plus tan squared theta. So this is nothing but sine of 2 theta. So sine inverse of sine of 2 theta, both the functions sort of cancel off, giving us 2 times theta. But what's theta? Tan inverse of x is theta, right? So we have y equals 2 times tan inverse of x. So now we can differentiate both sides with respect to x. We end up with 2 divided by 1 plus x squared, which is the derivative of the inverse tangent function. Well, let's do a way more solid example where our there is no way to do standard substitution. I mean, you don't have these quadratic terms, you don't have these x squared fancy terms to work with and interpret it as a case of using standard substitution. You'll have something that's way off, way different and way unique. So we have y equals the inverse tangent of 4 times root of x divided by 1 minus 4x. Now, since there is no x squared, there is no scope to do standard substitution. So we need to just convert this into some identity. But of which trigonometric function? Well, the inverse tangent gives it off. Since there's an inverse tangent outside, we need to convert the inner argument into some identity of the tangent function. That's only when the inverse tangent and the tangent are going to cancel off, right? Only when we have a tangent inside as an argument to the inverse tangent. So let's just rewrite this thing. We have the tan inverse of, well, what's 4 times the square root of 2? It's 2 times the square root of 2 plus 2 times the square root of 2, square root of x, sorry. We have 1 minus 2 times square root of x, the whole thing squared, right? Because that's exactly what 4x is. We have, when we square this, we have 4 times square root of x squared, which is x, so 4x, so we get that. So we can write this as the inverse tangent of 2 times 2 root x divided by 1 minus 2 root x, the whole thing squared. Well, what identity of the tangent is this? Does this look like? Well, let's recall that double angle formula for the tangent tan of 2 theta was 2 times tan of theta divided by 1 minus tan squared theta. So instead of a tan theta, we have a 2 times square root of x here. So let's just make that substitution. Let 2 times the square root of x equal tan of theta, so that we have inverse tangent of 2 times tan theta divided by 1 minus tan squared theta. So as I said, that's just the double angle formula for the tangent. So we have the tan of 2 theta. The tangents and the inverse tangent are going to cancel out each other. So we have 2 theta. But what was theta? Theta was the inverse tangent of 2 times the square root of x. So 2 times the inverse tangent of 2 times the square root of x. So we end up with something that's way simpler to differentiate. Let's differentiate now finally with respect to x on both sides. So we have 2 times the derivative of inverse tangent of 2 times square root of x. Looks like another chain rule now. So we have 2 times 1 over 1 plus variable squared. So this thing squared we know was 4x times the derivative of what was inside. So again, 2 is a constant. Derivative of square root of x is 1 divided by 2 times the square root of x. And then we end with the chain rule. So one of these 2's are going to cancel out over here. So we end up with 2 divided by square root of x multiplied with 1 divided by 1 plus 4 times x. So when our standard substitution would not work, our conditions for standard substitution were not being satisfied, we just compared this to some identity of the tangent. Why a tangent? Because this inverse tangent outside gives us a clue that we want something of the form of in the form of tangents inside as an argument, so that they cancel out each other eventually over here. So let's do more examples of completing the formula, because we completed this formula, right? Here it was the double angle formula. Let's see other examples. You ought to know your trigonometric identities really well to master these kind of derivatives. So we have y equals sine inverse of 3x minus 4x cubed. Well, again, no scope to do standard substitution, no x squareds around. So, well, is there any identity over which function now? Well, we have a sine inverse outside, so we need an identity over sine. So identity of sines inside, so that eventually they'll cancel out. So let's recall that the triple angle formula of sine. So sine 3 theta is 3 times sine theta minus 4 sine cubed theta. Well, we have a similar form here, but instead of the x, if we make a substitution of sine theta, we'll end up with this form. So let's do that. So let x equal sine theta. So we have y being equal to sine inverse of 3 sine theta minus 4 sine cube theta, and that's just the sine of 3 theta. So sine inverse of sine of 3 theta, sine inverse and sine are sort of going to cancel out. We have 3 theta being equal to y. What was theta then? Sine inverse of x. So 3 times sine inverse of x. Now differentiate both sides with respect to x. So we have the derivative of 3 times sine inverse of x with 3 divided by square root of 1 minus x squared. No chain rule, just straightforward derivative of the sine inverse function. Okay, final one now. We have y equals the inverse tangent of 3x minus x cubed divided by 1 minus 3x squared. Again, no scope for standard substitution, but we have a tan inverse outside. So making a substitution of x being equal to tan theta seems reasonable, right? So we have y equals tan inverse of 3 times tan theta minus tan cube theta divided by 1 minus 3 tan squared theta. But this is nothing but the formula for the triple angle formula for tan. So we end up with tan of 3 theta, the inverse tangent and the tan are going to cancel out to give us 3 times theta. Theta is tan inverse of x. So y is equal to 3 times inverse tangent of x. So now differentiating with respect to x gives us 3 divided by 1 plus x squared. So hopefully you can see when standard substitution fails and when we can totally use it. But you have to know your trigonometric identities really well to master these type of questions. I said that before. So this is the last type that we're going to deal with, which is called finding the common hypotenuse. So say we have y being equal to cosine inverse of sine of x plus cosine of x divided by square root of 2. Well, there's nothing that we can do literally in terms of substitution. No free x's. We have sines of x and cosines of x inside. But what we can do is split this into sine of x times 1 over root 2 plus cosine of x times 1 over root 2. Well, what does this remind us of? Are there any more formulas for the cosine that we can use? Well, the answer is yes, because recall what was the cos of a minus b. So cos a cos b plus sine a sine b. So we have all of these things. We have, say, instead of a we have an x, so we have cosine of x times cosine of b is somehow 1 over root 2 plus we have a sine of x and a sine of b is nothing but 1 over root 2. Well, how can we let some call it angle? So say cosine of b equal 1 over root 2. We need to find b, right? So that we can make an appropriate substitution here. Well, you may remember that cosine of pi over 4 is 1 over root 2. So b is pi over 4. But does that satisfy our sine of b equals 1 over root 2? Yes, it does, because sine of pi over 4 again is 1 over root 2. So instead of 1 over root 2, let's just make these appropriate substitutions now. So we have cos inverse of sine x times the sine of pi over 4 plus cosine of x times the cosine of pi over 4. So as I said, this is nothing but the sum of angles formula for the cosine. So we have cosine of x minus pi over 4. So cosine inverse and cosine are just going to cancel out. We get x minus pi over 4, and this is great because we don't even need to do any more substitution. We just have a simple x. So y is nothing but x minus pi over 4. So let's differentiate with respect to x on both sides. We have the derivative of x minus the derivative of pi over 4. Pi over 4 is just a simple constant, it goes to 0. Derivative of x is 1, and calculating derivatives couldn't be easier. So all of this inverse trigonometric junk just finally becomes 1 on differentiation. How nice, how elegant. So let's do a last one, and you will see why this method is called finding the hypotenuse. So if you have the sine inverse now of 3x plus 4 times square root of 1 minus x squared divided by 5. Well, looks like we have a standard substitution model over here. So let's make that substitution. Let x equals sine of theta. So we have y being equal to sine inverse of, let me write it this way, 3 upon 5 times sine of theta plus 4 upon 5 times square root of 1 minus sine squared theta. So we have y being equal to sine inverse of 3 by 5 times sine theta plus 4 by 5 times this evaluates to cosine of theta. Well, now the hint for using the technique of finding a common hypotenuse is to have a common denominator, because 5 acts as that common hypotenuse. Because like the previous question, we want to use some property of the sine because we have a sine inverse. So let's refer to this formula, sine of a plus b. So that becomes sine a cos b plus cos a sine b. So we have sine a. So if you have a equals theta, you have sine a over here, and a cos b. So cos b should equal 3 divided by 5, and as we said, a is theta, so cos a we have that over here, cos theta, but we need sine b to equal what we have here, 4 by 5, right? And the best part is, say if you have 1 minus cosine squared of b, it should become sine of b, right? And that's what exactly happens. You have 1 minus 9 by 25, that just evaluates to 16 by 25 under root, that becomes 4 by 5. So now let's make a triangle over here for visualization purposes. You have this 90-degree angle here. Let's call this angle beta. Or let's just call it b, since we already defined everything to be b. Let's call it b. So as I said, the cosine of b is 3 by 5, which means the adjacent side should roughly equal 3 and hypotenuse should be 5, and Sine of B is 4 by 5, so opposite side is 4 and hypotenuse is 5. And the best part is, since they satisfy a Pythagorean triplet, so they are a Pythagorean triplet, that's why you can have this triangle over here. This triangle can exist, this right angle triangle can exist, because these three numbers satisfy Pythagoras theorem. So what that says is, let's make a fresh substitution. Let cosine of B, as I just showed you, equal 3 by 5 and sine of B equal 4 by 5. And these assumptions are valid because they satisfy Pythagoras theorem. They satisfy Pythagoras' theorem. So you can have indeed a right angle triangle like that, and it's valid to define cosine of B as 3 by 5 and sine of B as 4 by 5. Because and the hint before using this approach was, the hint was this common denominator 5 that acts as a common hypotenuse. So that tells us that they should be part of a same triangle. So this sine inverse of, we call this B, right? So cosine of B times sine theta plus sine of B times cosine of theta, that becomes sine inverse of sine of B plus theta, right? I just showed you the sum of angles identity, so you can get rid of the inverse sine and the sine. This B plus theta being equal to y, and what was our theta? Sine inverse of x, right? We had x's before, so this translates to y equals B plus sine inverse of x. Well, B is just some definite angle, right? It's a constant, right? Because we have 3 by 5 and 4 by 5 as well defined numbers. So B is essentially cosine inverse of 3 by 5. And if you plug that in your calculator, you'll get something in radians, right? So that's a constant. So B is a constant. So if you differentiate everything with respect to x, B just becomes 0. We only have the derivative of sine inverse of x, which becomes 1 divided by square root of 1 minus x squared. So if you have like sum of two things and a common denominator, then this method of finding the common hypotenuse is extremely beneficial. So I hope you enjoyed this video. I hope you had fun evaluating these derivatives in a smart way, and I hope you use a similar techniques when you're doing your practice problems, because believe me, it will save a lot of time, lot of energy, and it's always nice to see elegant methods being used to solve mathematical problems. So please like, share and subscribe to my channel. Recommend me to your friends or people who just want to learn calculus, your juniors maybe. And stay tuned for my next video. Stay in, stay safe, have a great day. Peace out.